I left off a negative sign there. Which is silly of me because the negative always follows cosec. So anyway, make sure you've updated that on your table. I wrote it down right when I was working it out and then I forgot to put it here. So, there's our basic functions, our reciprocal functions. Let's do our inverse ones. And I figure I should redo this with you. Number one, because some of the later questions will deal with them. And number two, I remember when we were in related rates, and I said, hey guys, remember the derivatives in the inverse trig functions? And everyone gave me this sort of blank stare. So, let's just re-get them. They're not that hard to get. And also, this is an opportunity we can use implicit differentiation to work these out, even though it doesn't work out to be that different. So, before we dive into doing these, there's a little bit of, there's a couple of identities which will help us to simplify these results, okay? So you start with the Pythagorean identity. This is where so many other results come from, right? And if you wanted to get sin x or cos x on their own, out of this identity, what would you do? Well, for sine, you'd kick the cos squared over, and then you would take the square root, right? So I'm going to put that down. That's 1 minus cos squared. Is that okay? And in the same way, I can do that for sine. So 1 minus sine squared. Okay? This will become handy later. I don't know if you recognize these as forming parts of the denominators of the derivatives for the inverse trig functions, but they'll come up in a second. And then secondly, when you take your whole identity and you divide through by cos squared, this is an important one because this is what relates sec squared and tan squared. That's a familiar one, right? But in my case, when I get to inverse tan, I actually want cos squared. So I got to this line by dividing every term by cos squared, but now here, I'll just take the reciprocal of both sides. So I'm going to end up with 1 plus tan squared over here, okay? Right, now, when we start on something like y equals sine inverse, because I don't know anything yet about sine inverse, I want to get it in terms of functions I do know about, like say sine and cos, okay? So let's do that. I'm going to have to take sine of both sides, which leaves you here. Okay? Now, before in our earlier proof, you may remember what we did was instead of taking dy on dx, we differentiated instead with respect to y. So I took dx on dy and then I flipped things later on, and that worked fine. Okay? That's still a fine method to do it, to get this result, but because you guys know how to do this implicitly, maybe we should give that a go, since we are after the derivative with respect to x, after all. Okay? So I'm going to take the derivative of both sides with respect to x. Okay, this is the way implicit works, do you remember? Now, on the right-hand side, the derivative of x is just 1. Okay, so that's what you get. And on the left-hand side, remember the key to implicit differentiation is to think of that y as a function, because, you know, that is what it is, right? So if it's a function, this is a function of a function, it's chain rule, okay? So what you do is you differentiate the inside first, which is just dy on dx, yeah? And then you differentiate the outside. The outside function is sine, so I'm going to end up with cos. Right? Okay, now what was I after? I was after dy on dx. Okay, so I'll bring that over the other side, cos x. Okay, and now you can see why I was bothering with this result here, because I want to get things back in terms of sines, because that's what my original function was defined as. Okay, so I'll write this as the square root of, 1 on the square root of that, right? Except sine x is just, wait, where did I write it? Sorry, you guys missed it. That's a y. That's better. Always tricky with your variables, which ones you've got, so be careful with implicit. Sine y is just x, right? So that's why on the bottom here I've got the square root of 1 minus x squared. Okay? So that's the general pattern of how it works. You can actually see the implicit bit doesn't hang around for very long. The rest of this is exactly the same as if you'd gone from here and taken dx on dy. Okay, really quickly, even though you can probably anticipate the result for this off of what we got for sine inverse, let's do it again because it's not that hard, and I'll give you some practice with implicit. What do I do here? Let's skip this step because I think you guys can see it. Let's do it in our heads. On the right hand side, when I differentiate with respect to x, I'll just get 1. Over here, when I differentiate, I've got chain rule, so I'll do the inside, which gives me dy on dx. And then I've got the outside, which is minus sine, right? So minus sine y. Then, as I did before, I'll toss that over the other side. Okay, and now I use this identity here. Minus 1 over And of course, cos y is just x. So that's how you get this result. Which is exactly what you ought to expect, because these are really the same graph, but in reversed. And of course, they're shifted up and down as well. Okay, last one. Here we go. Take tan of both sides. And now we differentiate implicitly. So on the left-hand side, I'll do the inside, which gives me dy and dx. Then you do your outside, which gives you sec squared, right? Because it's just tan. So sec squared y. And then differentiate the right-hand side gives you 1. So dy and dx, I'm going to multiply through by cos squared. And that's just this, right? You see that? So dy and dx is 1 over. And this is why it has no square root signs. Okay, that's how you remember that this is the different one. Tan y is just x, so ta-da! So, not too difficult, okay? We are going to be doing a lot of work with integrals that start like this, okay, where you've got to integrate something like this, and that therefore we're going to end back up with sine inverse, cos inverse, tan inverse as the primitive function, okay?